present this screen and see. Tell me if you guys, can you see it? Give me a thumbs up if you can see that screen. Perfect. Okay, so this is a related rates question, and they're usually some of the hardest questions that we have to do, because I think people get confused about the notation and what does it mean, and as long as you kind of keep the notation straight, then I think that that these aren't terrible to do. And then this one actually kind of morphed into a separation of variables, which we should go over anyway. So it was a good thing to kind of go through. So on this, you got this cylinder. Some of the things that are really important is there's I mean, it goes through and it talks about some valve. This first part kind of sets up the problem, but I don't know that it's terribly important information. Like if I didn't read the first two sentences, I don't know that it would. I still think I could do the rest of that problem. But so I kind of started with the things that I would want to know would be the rate of change of the height of the water in the barrel with respect to time is given by that. So that's just a derivative of the height of this thing with respect to time, where H is measured in feet and T is measured in seconds. That's kind of important, because then that will help you when you figure out if you've differentiated or if you've integrated, or if you're now talking about volume, what the unit of measure is going to be. So usually there's some kind of unit of measure that is in the stem of the problem that they would expect you to use. And then fortunately, you didn't have to worry about memorizing the volume for a cylinder. It's given right there. So then they jump in and it says, so if we kind of jump into part A, it says on here, find the rate of change of the volume of water. So if we think about what that is, that would be dV dt. Okay, so that's the rate of change of the volume. The d in front of the v is the derivative of v. The d in front of the t is with respect to time. So that whole idea is the rate of change of the volume of the water. That's what we're supposed to figure out. And we're supposed to do that when the height of the water is 4 feet. So the idea behind that is H is equal to 4. And then finally, they kind of say, in our answer, we better indicate units of measure. So the piece of information that we're given is we're given the height is equal to that. We're given dH, dt is equal to -1/10 times the square root of h. And I'm not going to write it as, because I know I'm going to have to differentiate that at some point. So I'm going to write that as h to the 1/2. And I'm also given that there's a volume equation, pi r squared times h, which, as soon as I write that in there, I should be thinking in my head that I probably am going to have to use the product rule. So right away, there's a product rule in there that I know I'm going to have to kind of invoke. Because if this is the equation that I have, and this is the question that I have, I know I'm going to have to differentiate. I know I'm going to have to differentiate that equation to get this idea behind dV dt. So that's what I'm going to do in part A, is I'm going to say, okay, for this, got all this information. If I differentiate the V, I get dV dt. If I differentiate the right-hand side, I have to use the product rule. So I have pi times 2r. But remember, anytime you differentiate a variable, you have to have the derivative of that variable with respect to time, because time is a brand new variable that we're kind of introducing into this equation that doesn't have anything to do with time. At least at the moment it didn't. So then plus, then we'd have pi times r squared, then times the derivative of h, which is dh dt. So that's our derivative of the volume equation. That's this volume equation right here. That's this volume equation. Differentiated would show up as that using the product rule. Any questions on that before I kind of move on? So at this point, you kind of actually have everything that you need in this problem. There's a couple of things that you got to kind of realize, though, on this, is if we go back up to this thing, we know in the stem of this problem, we know that r is equal to 1 foot, because if the diameter is 2 foot, the radius is 1 foot. And the other thing we know is the rate of change of the radius with respect to time is always going to be 0 feet per second. And the reason it's 0 is the radius doesn't change. You know, no matter how full that cylinder is, whether that cylinder has 4 feet of water in it or whether that cylinder is filled all the way to the top, that rate of change of the radius is 0 because the radius literally doesn't change. It can't. That cylinder is not expanding. It's just either filling up or draining with this water that's going in here. So with those pieces of information, you know, we have, at this point, we have this piece of information, we have this piece of information, we have this piece of information now in the stem of the problem. We know that h is equal to 4. If I highlight this piece again, that's there. And we know that this is what we're supposed to find. So with all those red highlighted things, we actually can put in everything into this equation and leave it alone. We don't have to do any simplification on it. We can actually just jump right to an answer on this. We can say dv dt is equal to pi times 2 times 1 times 0 times 4. So that's the first part of that equation. Pi, and then the radius is 1. The rate of change of the radius is 0. The height of this thing that we're supposed to be talking about is when h is equal to 4. And then if we keep on going on this, we have plus pi times the radius squared times, now this, we have this dh dt. Well, we have an equation right here for dh dt, and we know with that and with the fact that h is equal to 4, we can just plug those values in. So right in here for dh dt, we can plug in, I'm just going to surround it with parentheses because of that negative. I don't want somebody to think I'm doing subtraction, times 4 squared. Or sorry, 4 to the 1/2. I don't have to simplify that. I can leave that just the way it is. All that's in there at this point is arithmetic. I don't have to simplify it. I shouldn't simplify it. I know that I could if I needed to. I'm pretty confident you could do 1 squared. I'm pretty confident you'd know that the first part of that thing is 0. You maybe even can jump to the fact that 4 to the 1/2 is 2, but there is no need. You just leave it alone. That is the answer for part A. Any questions on that I can help you with? All right, let's go to part B then. So on part B, When we look at part B, I just kind of copied the whole thing down here to try to get ready for you today. So I left the stem of the problem in there because I think I'm going to use it a little bit more, maybe. And so, you know, when we go to this question right here, and I'll just use blue to highlight it. When the height of the water is 3, oh, actually, let me back up for a second, because I didn't indicate units of measure, so I actually wouldn't have gotten full credit for this. The units of measure on this is the rate of change of volume, right? So the unit of measure on this is a derivative, so you know it's going to be per seconds because the time measure is in seconds. But since this is a rate of change of volume, that's going to be feet cubed. Is the unit of measure on this, is feet cubed because it's volume, and then per second because it's a derivative. Okay, so let me move to this one. So when the height of the water is 3 feet, they're kind of saying, well, what is the rate of change of the height? Is the rate of change of the height with respect to time increasing or decreasing? So the question is, when h is equal to 3, is dh dt increasing or decreasing? So right away, when you think about, like, what do we do with this? As soon as you see this, you should think the chart. The chart is going to be kind of the key component on this. And when you think about, like, the chart, and you think about where we have this chart, anytime we write increasing here, we write positive here. Anytime we write decreasing here, we write negative here. So if we just relabel our columns, when we're trying to figure out when dh dt is increasing or decreasing, we know to get to that next column, that means we're going to take the second derivative of that, or we're going to differentiate that thing we have. So we're just going to differentiate whatever we have to get to figure out, and then we're going to figure out, is that thing positive or negative when h is equal to 3, and then we can determine whether or not dh dt is increasing or decreasing. So it's kind of taking this idea behind the chart and adapting it, and then we're going to use that for our reason in the result. So we go back up, and in this problem, we're given that dh dt is that value, so that's what we have to differentiate. So we're going to go over here, and we're going to say, okay, well, if we need to differentiate that, what we're going to do is we're going to do, remember, this is the notation for the second derivative. That notation right there is the second derivative. That's the second derivative notation. So we're just going to differentiate this equation right up here. We're going to differentiate that equation. And so we got -1/10. That's the constant that just comes along. We don't change it. And then remember that this equation is -1/10 h to the 1/2. So if we differentiate that, we drop the power down. We reduce the power by 1. But since we're differentiating with respect to time, we put that in there. Okay? Well, notice that is that equation that we were given, that dh dt. So we actually could rewrite this as -1/10 times 1/2 times h to the -1/2 times -1/10 times h to the 1/2, because that was the original equation. That's what dh dt is. You know, if it goes to here, you know that's that equation right there. So we can just insert it in there. And now the only thing left is to plug in 3 in there and to kind of determine, is this positive or negative? When we go into this equation and we start plugging in 3, we're looking at, dh, or d squared h dh dt squared when h is equal to 3. H is equal to 3 is negative 1/10 times 1/2 times 3 to the negative 1/2 times negative 1/10 times 3 to the 1/2. And this value is greater than 0. That value is greater than 0 because we got a negative here, we got a negative here, so that value is positive. And so in the end, since since the rate of change of the height, the second derivative of the height, is greater than 0, dh dt is increasing when h is equal to 3. So that's part B, is that information right there. Any questions on that I can help you with? Okay, so then we'll just move on. Let's look at the last part. And on this one, we're going to go through some steps. We haven't done this for about 4 weeks, 4 or 5 weeks. This idea behind separation of variables to find this expression. Okay, so there were 6 steps to separating the variables that we need to kind of cover. So step 1 is to get the variables on either side, or sorry, I should say, get the variables separated by using multiplication and division only. Along with that, don't move constants that are multiplied. Anytime you start moving constants that are multiplied, it's just extra work, and you probably will run into some kind of an issue that you'll kind of screw things up. So that's the idea of that negative 1/10. I'm going to leave that over on the right-hand side. I'm never going to move that to the left-hand side. That remains on the right-hand side all the time. The second thing is to integrate the left and the right side. So you're going to integrate the left side, you're going to integrate the right side. The third thing that you're going to do is add C to the right side. Okay, so you're not going to add it to the left side, you're just going to add it to the right side. Technically, you'd add a C to the left side and then a C to the right side, but in the end, you're just adding some constant that you have to account for. Step 4 is use the given point. There's some kind of point that they will give you. So use that point to find the C value. And the last thing that you need to do is solve the equation for the, and I'm going to put it in quotes, the y variable. Whatever the y variable is, whatever that independent variable is, or the dependent variable is, That's what you're going to solve for. So we're going to go through all five of these steps with this problem, and I'll try to do it over here on the side here, so it's kind of in line here. So in this, we're given this equation right here. That's the equation that we're supposed to separate. Now, if you look at it, at time t equals 0, the height of the water is 5. What that they're giving us there is that's that point 0, 5. That's what we're going to use to find c. Okay, so that's what that thing is right there. Now, we're going to take this equation, dh dt, which is -1/10, and I'm going to write this as h to the 1/2 because I'm going to have to integrate at some point in time, and so I want to make sure that I have it in a form that I can integrate. So the first thing I'm going to do is I'm going to get the variables separated by multiplication or division and only moving variables. I would never move a constant. So if I think about what this would be, then if I divide by h to the 1/2 and leave the -1/10 over here, and I move the dt over there, that step, I have moved everything that involves h to the left side and everything that involves t to the right side. Any questions on that step? Okay, so the next thing I'm supposed to do on this is I'm supposed to integrate the left side, and then I integrate the right side. Integrating the left side, I can do that because remember, this is the integral of h to the -1/2 dh is equal to the integral of -1/10 dt. So if I integrate the left-hand side, I would have h to the 1/2 divided by 1/2 is equal to -1/10. That's just a constant. We don't get rid of it. We keep it. We now have a t variable in there. And then we're going to add plus c. So that line right there actually is both steps 2 and 3. I've integrated the left side, I've integrated the right side, and I've added the plus c in there. Any questions on that? Okay, so now we're going to use this point that we were given. That point we were given was 0, 5. We're going to use that point to figure out what the c value is. So then we can go back and solve this expression for that y variable, which in this case, the y variable is h in this case. So we're going to use 5 for h and 0 for t. So this would be 5 to the 1/2. And I'm purposefully not simplifying just because I don't need to. I was always told not to simplify. So in this case, c is equal to 5 to the 1/2 divided by 1/2. I understand that if you were like, wow, I really hate the way that looks, I want to write that as 2 times the square root of 5, I would be fine with it. But I'm not going to do it because I've told you all along, never simplify. So now this last step is going to be to take this equation and this constant, put those things together, then solve for h. So what we have is we now have this equation. We have h to the 1/2. Write that a little cleaner. H to the 1/2 divided by 1/2 is equal to -1/10 times t plus 5 to the 1/2 divided by 1/2. And if I go through and solve this, in order to solve this for h, the first thing I would do is I could multiply both sides of this by 1/2. And that would get me that would get rid of divided by 1/2. So I could write, well, that means h to the 1/2 is equal to 1/2 negative 1/10 t plus 5 to the 1/2 divided by 1/2. If I'm not simplifying, that's what I have. And then finally, to get h all by itself, to get rid of that power of 1/2, if I square both sides, would 1/2 times negative 1/10 t plus 5 to the 1/2 divided by 1/2. And then I am going to square that. And that would be my solution. And I don't have to simplify it. I know that there's some simplification in there. You could make it, negative 1/20th t plus the square root of 5 squared if you wanted to. You don't have to on the exam, so don't bother. Just write neatly and make sure you copy whatever you had on the previous line, but that's a fine answer the way that's written. Any questions on that? We did that the first week of distance learning. Was when we did that. Even we did that before spring break, I think, was when those notes were. So if you look back, the assignment maybe even was in Google Classroom, honestly. But the idea behind that separation of variables, that's something that I would maybe expect them to make you do, because this is one of the problems that AP asked me to go over with students before you take the exam. But so those 5 steps that are in blue, pretty important, just to have those with you when you're taking this exam. And you can even go back, and even though you've seen me do this problem, pull this problem aside and rewrite it on a piece of paper and see if you can separate the variables and do it. And my guess is you're going to find that it's not that you go, oh yeah, I remember doing that now, but we haven't done it for a few weeks. And so I think it's pretty good timing that we did it today. Any questions on any of that? Okay. I just stopped the recording.